Well, now we're going to start the discussion of Newton's second law. And as we briefly introduced in the last chapter, Newton's second law states that our net force is equal to the mass times the acceleration. So Newton's second law basically provides us with the information of where our acceleration comes from for an object. It comes from some net force that's acting on that object. So briefly here, we're going to be using Newton's second law to find an object's acceleration. Then we're going to take that acceleration and answer questions about the object's motion using the kinematics equations that we learned in chapters 2 and chapters 4. Or vice versa, depending on the problem statement. And we'll see some of these definitely in homework and possibly in examples as well. So we have to go through the requisite problem-solving strategies when we're dealing with Newton's second law, when we're dealing with some body that's undergoing acceleration. And the first step, as always, is just to draw a picture here. You guys see this? Okay, thank you, Dan. Yeah, please let me know. Please let me know. That's better, huh? Now it feels dark in here. It is dark. Oh, well. Okay, so we want to draw a picture. So this is all the basic steps that we've covered several times before, and we certainly covered yesterday, where we drew our picture, we identified our points of contact, then we went to draw a free body diagram, identifying our contact forces and our long-range force, and then in the case of dynamics problems, we've got one more additional step. Because of the fact that we're undergoing acceleration, we're often going to find that it's useful to draw some kind of motion diagram to explain that motion, to visualize that motion. After we get our pictorial representation taken care of, we can go ahead and move on to our mathematical representation. You know, Newton's first law says that the sum of our forces is equal to 0. Newton's second law says that the sum of our forces is equal to mass times acceleration. And we can evaluate this vector sum of our forces directly from our free body diagram. And the last two statements on this slide here, it says that once we have the net forces, we can find the net acceleration. We solve for that acceleration, then use our kinematics to find velocities and positions as requested according to what problem we're working on, or if the problem is given in the opposite direction and telling you something about the motion, we can solve for the acceleration given certain information about the motion. Then once we have the acceleration, we can turn around and solve for, say, the net force on some object. So we can go either one way or the opposite way, depending on what our problem statement is. And again, our forces are telling us why an object moves. Kinematics is how our forces describe why our objects move. Okay. So basically, the best way that I can tell you guys, that I can show you guys information about Newton's second law is just to actually work through examples. There's not a whole lot more to be said, honestly, than what I just said. So let's take a look at some example problems. The first one I have here, I've got a 20-kilogram crate on a 20-degree slope. My slope, or my incline, is 50 meters long. I've got some frictional force of 30 newtons opposing motion. And my question here is I want to find the speed of my crate at the end of the slope. And I should say here that my crate starts from rest. Okay, so first thing I do.
Draw a sketch. Draw a picture.
Yes, thank you. Thank you for playing along. So we've got our slope here. Our slope's at 20 degrees. We'll put our crate there. I need to define my x and my y directions. And as we've said a few times when we're dealing with inclines, we put the x-axis so that it has the same slope as my incline does. So my x-axis goes along my incline. I can label some specific points of interest on my sketch, just like we did with the kinematics problems. This here is x naught, v naught, and I'm interested at my end point here, the end of my slope. So I can call this x1 and v1 down here. So after we've got this pictorial representation, we can go ahead and draw a free body diagram. What forces are included here on my free body diagram?
Gravity, friction. Normal force, friction.
Okay, gravity, normal force, and frictional force. So my contact forces, I want to write down first. Remember our normal force is always perpendicular to my surface. So my normal force is going to be pointed this way, always perpendicular to my surface. My frictional force is going to be opposing motion here. And gravity always points down towards the center of the earth. From this point, I can start to write down some principles that I'm going to use to solve this problem. So we're talking about Newton's second law. Well, that makes sense. I'd write down Newton's second law. So I can write down Newton's second law. I can write down my principle of superposition. And I'm also going to be using kinematics in the final steps of solving this problem. Next step that the author of the textbook has taught us is to write down our knowns and our unknowns. So my knowns here, I can set my x0 equal to 0. My x1 is equal to 50 meters. My frictional force, I said, was 30 newtons. My mass of my crate is 20 kilograms. And my initial velocity in my x direction is 0. And I want to find, what is that final velocity of this v1? So now I've got basically all the first steps of my problem done. And I need to turn to a mathematical solution. So what's the first thing I do here? Good idea.
I would find some units of gravity.
Yeah, thank you. Yeah, we want to break down our force vectors into x and y components. So very common here, very common. Not just in our force problems. This idea was common in our kinematics problems. We want to break our problems down into x and y components. So we're going to break our forces down into x and y components. So we've got the force of gravity pointed straight downwards here. And our x-axis is this way, our y-axis is this way. So now we need to figure out how to break our gravitational force down into x and y components. So what's that?
Oh, rather.
Okay. I'm glad to hear that, actually. I'm not glad that you messed up, but glad that I didn't.
Oh, okay.
Okay. So we can draw out our right triangle here, representing our gravitational forces in x and y. So this is our right triangle. I'm going to move this over to the side a little bit here. We can say that this, on our bottom leg, is Fg sub x. This is Fg sub y. And we'll look at a little geometry here. That angle right there is 70 degrees. This is 20 degrees. My angle right here is 90 degrees. That makes this angle 70 degrees. If this angle is 70 degrees, well, I've got a right angle here. That makes this angle right here 20 degrees again. So my angle right here is 20 degrees. Same angle as the slope of my incline here. So if I write out my x component of gravity, I can see that this is opposite my 20-degree angle. If it's opposite my 20-degree angle, SOHCAHTOA, I'm using sine equals opposite over hypotenuse. I'm using sine. So this is sine of 20 degrees. Same thing with my y component. This is cosine of 20 degrees. My y component is adjacent to my 20-degree angle, so we use cosine. Cosine equals adjacent over hypotenuse. Okay. So this is my gravitational force. Now we see that the normal force is just directed in y. My frictional force is directed in the negative x direction. So I'm done now breaking my forces into x and y components. The other two are already taken care of. So what's the next step? What's the next thing I should do here?
On that force?
Yeah, find the net force. Can we be more specific?
Out of all the vector components?
Okay, okay. You mean in the x and y directions? Yeah, yeah. Yeah, I'm digging for answers that you know, but it's hard to know what I'm digging for sometimes. Okay, so we're going to look at the sum of our forces in the y direction, sum of the forces in our x direction. So even though we don't really need it to solve this problem, I want to take a look at the sum of the forces in the y direction. Well, we know that the sum of the forces in the y direction has got to be 0. My box is not going to be moving in my y direction at all. My box is sitting on that slope. The x-axis goes along that slope. That means my box is going to sit at y equals 0 all the way along its motion. If it weren't sitting at y equals 0, that means it would be magically floating off the slope or somehow merging with my material that my incline's made of. So impossible. So the sum of my forces in my y direction is equal to 0 here. So let's take a look at what those are. So I've got my normal force plus my force of gravity in the y direction. And when we start to fill things in, we of course know that I've put plus Fg sub y there. This is a negative mg. So we look at our free body diagram. We see that gravity is pointed, our gravitational component, our y component of our gravity is pointed in the negative direction. So we've got to put a negative sign. So I'm just going to go ahead and solve for the normal force here. Our normal force is Fg cosine of 20 degrees. Or what we'll learn, or what we did learn yesterday, is that this is Mg cosine of 20 degrees. And I did this because this is a common thing that you see in these problems. When we get into friction, you'll need to know what the normal force is to actually calculate your frictional force. So it's good to know how to figure out, what the normal force is. It's, in this case, just mg cosine of 20 degrees. So on to the problem we're actually doing here. The sum of my forces in my x direction, Newton's second law, is m times my acceleration in my x direction. If we look at these forces, you see that I've got here my force due to gravity is pointing down my slope to the right on my x-axis. We see that we've got the frictional force. It's pointed to the left. That's all the forces we have in our x direction. We can fill in expressions here. I've clearly done something wrong on my notes. That's sine of 20 degrees. Minus f sub k equals mass times acceleration in the x direction. Now, looking at this, f sub g, that's just mass times gravity. I'm given the mass. My f sub k, I've been given as well. That's 30 newtons. Once again, I'm given the mass. So the only unknown I have in this equation is my acceleration in the x direction. I just need to solve this equation for my acceleration in the x direction. Doing that gives me ax is equal to fg sine 20 degrees minus f sub k over my mass. So I can go ahead and fill in mg for my f sub g. And when I fill in numbers here, maybe next line. I get an acceleration that says acceleration is equal to 1.85 meters per second squared. So this was just all about using Newton's second law and then solving for my acceleration in the x direction and putting in what's given in the problem statement. So once I've reached this point, I've kind of started to lose track of actually what we were solving for in the first place. What was it we wanted to find? Okay, yeah, final velocity at the end of the slope. Okay. So now we need to turn from Newton's second law to what we learned in kinematics. So kinematics with ax equals 1.85 meters per second squared. And just to write it down again here, we've got our slope, we've got our box, and we want to find out what the velocity is at this point down here. Any suggestions? Yeah, I think yes, yeah, absolutely. At least one of you said the right answer. and probably the other one said something that can certainly get us there. I think the easiest path to take in this case is to say v1 squared equals v naught squared plus 2a times delta x. I should be complete here and put my subscript x on my acceleration. probably should put subscripts there. So initially, my crate is sitting at rest. So my V naught's 0. Okay? We know that the acceleration, we just solved for that. We know our delta x here is 50 meters. That was given in the problem statement. Right there, 50 meters long. So we can fill in our values. V1x squared equals 2 times 1.85 meters per second squared times 50 meters. When I do the math and take the square root, I get that my velocity at the bottom of this slope is 13.6 meters per second. So that's one example of the kind of problems you'll be asked to do in this chapter. And it's one example of the analysis we can do to solve for motion given a certain set of forces. All right, this is a good time to mention this. Problem on the test. You know, it's easy to get lost in all the mathematics standing up here and lose track of what we're actually doing, but what we're doing is we're taking and observing things we see in the natural world and applying mathematics to learn about their motion, basically to be able to describe how they're going to behave and how they do behave. So one of the problems on the test said that you have 2 balls or 2 rocks. Problem number 4 on the multiple choice. And they were both released at the same time. The first ball was just dropped. The second ball was thrown downwards at some speed. And the problem asked about, well, what's the time difference between ball 2 striking and ball 1 striking? And one of the options was actually, well, they both hit at the same time. And several of you all chose that option. And I think it was because you were sitting in a stressful environment and possibly didn't fully visualize the problem. But that's the one thing that can't happen. They can't hit at the same time if one's released from rest and one's thrown downward. So, as we see there. Yeah, clearly the one that's thrown downward is going to hit first. And I just want to mention that to you because it's easy to get lost in the math and forget about the actual real world and what's going on. And we need to keep in mind that we're describing what happens in the real world as we go through all this math. Any questions about this problem? Okay, so this one I thought was interesting.